What is up, multivariate gang? Today we are going to be talking about the properties of vector arithmetic. Now, what do I say when I mean property? I mean stuff like commutative property, additive property, stuff that you guys had for scalars. They have rough equivalents in vector arithmetic. So let's get down to it. First, before I talk about the actual rules, I would like to talk about the geometry of a couple of the rules. I'm using what several people like to call the vector addition parallelogram. All right. So we have a vector A. And we add it to a vector B. Head of the first, tail of the second, blah, 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 blah. We get this guy right here. Vector A plus vector B. Easy peasy. Right? Right. Now, say we've got vector B over here. And we've got vector A over here. Now, if we were to draw vector B plus vector A, we would start at this point right here and end at this point right here, which gives the exact same vector as A plus B. So, if we have a parallelogram where two sides are vector A, two sides are vector B, one of the diagonals is going to be vector A plus vector B, which is the same as vector B plus vector A. We've proved it geometrically, proved it-ish, I guess. Now, what about our other diagonal? Well, if we go from the head of B down here to the head of A, let's make that a different color. Let's make this green. From the head of B to the head of A, what are we doing when we're going from the head of the second vector to the head of the first vector? Well, we are subtracting. So vector A minus vector B equals, now, what if we go from vector A to vector B? If we're going from the head of A to the head of B, that means we're subtracting A from B. But it's going in the exact opposite direction as A minus B. This is A minus B. And that other one we drew was B minus A. They're going in the exact opposite direction. So that means A minus B equals negative B minus A, as you would expect. So this little vector parallelogram is makes it easier to remember shortcuts about the geometric nature of vector addition and subtraction. Cool. All right, now down to the actual rules. To these in orange. Vector U plus vector B equals vector V plus vector U. We just talked about that with our little parallelogram. That is to say that vector addition here, do a plus sign, is commutative. Order does not matter. And I'm going to give these without proof. And if you want to prove these to yourselves, they're all fairly straightforward. But I think you guys will just take me on my word with this one. So, this one right here, vector U plus vector V, then adding vector W, is the exact same as adding vector U to vector V added to vector W. Meaning that vector addition is associative. Associative groupings do not matter if they're all addition. Now, u plus 0. What is 0? 0 is the 0 vector. It's basically just like a dot. It has no components in any space or whatever. 2 space, 3 space, 4 space, 5 space, does not matter. It has 0 length in any direction, which means its direction is undefined. It's just a dot. So u plus the 0 vector is the same thing as 0 vector plus the u, which is just u. So vector plus 0 equals the vector. I'm going to just do it with the fishhook. Vector addition is identitive. Just like 1 plus 0 is 1, vector addition is identitive. If I can spell it right. All right. U plus negative u equals 0. I mean, that checks out, right? U minus u equals 0. Same. Checks out. That is to say that u's additive inverse is negative u. I'm not going to write that down. All right. K times LU equals KL times U, which is to say that scalar multiplication is also associative. Grouping doesn't matter. And it's not explicitly stated, but it's also commutative, in case you didn't catch that. Scalar multiplication times a scalar times u plus v is the same thing as the scalar times u plus the scalar times v. Another way of saying scalar multiplication is distributive. And again, if you don't believe me, just prove it. You can prove it yourself. And this is another way of saying that scalar multiplication is distributive. Not only can you distribute the scalar across vector addition, you can also distribute a vector across scalar addition. And of course, scalar 1 times u is the same as u. Which is to say that scalar multiplication is also identitive. Cool. Basic rules given without proof. Some of the proofs are in your book. I mean, these are all really basic, guys. I'm sure you could prove them to yourself any day of the week, so I'm just going to leave it here. Keep this video short. We've got one more video in this section. We're going to be talking about normalizing unit vectors. And then we are all done with this chapter. So, good job, guys. I'll see you in the next video.